Okay, here we are, the special one. So this is where we were last time. I talked about those constants. We talked about this parse number thing. Da, da, da. Why? We did this one, which has a weird two's complement thing, and then later when I was walking back to my office, I answered the question you asked about couldn't we just have done this first without having to do that extra check, and then I remembered why it was important to do it in this order, and I can't remember anymore right now, so it doesn't matter. But I feel like it's important. I just can't remember. No,
You change the number first,
but
and then you just check if.
well, because you need to know the number of bits.
The max doesn't change.
Yeah, well, it could, depending on the actual underlying system. I thought of a reason, I can't remember what it is now, but I'm pretty sure I answered it, but I'm not too worried about it right now. So the parse number, verify syntax. This is just a method that effectively, if we ever, it's a very side effecty one, but welcome to exceptions. Basically, take a program line and compare it to all of the things in the valid syntax. If it matches one of them, return the syntax. If it never matches any of them, though, we're going to raise an exception being like, we can't assemble this program. That's all. Okay? And then this is the main part of the, this is like now starts the main part of the script. So here's how I've got it like set up to start running. So those are just some like the constants and the helper functions. Now how does it go? Well, this will take command line arguments, okay? So either it's going to be 2 or greater than 3. Basically, if the number of command line arguments is wrong, it's going to raise an exception. It won't run. Your assembler can take 1 or 2 command line arguments. If it takes 1, it's the name of the file to assemble. If it takes 2, if you give it a second, it's the name of the file to assemble and the name that you want to call the output. If you don't specify a name, that like second argument, if you don't specify a name, it just calls it a.hex. Because, okay? And there we go. Here's some code on the usage. Like if this isn't true, we raise a value error, but we print out a message on like detailing how to use the assembler correctly. If you're saying like, well, hold on, the argv count will be, it includes the name of the file being run. So if you say like Python assembler, that actually counts as one of the command line like the name of the file is one. It's a funny little thing. So that's why if you're like, wait, the counts don't make sense. It's fine. The assembler takes 1 or 2 command line arguments, okay? And then with open file, read the file. We're doing some parsing here. We do some stripping for each line. We read the line. Anyways, we just read the file, strip out any extra white space we don't need. We check to make sure that the program is not bigger than 16. If it's bigger than 16, it won't fit into our RAM, so it crashes. And then after that, this is the main loop. Machine code, we're basically going to make a list of all of the machine code lines. We're going to take the program list, take the raw program line, raw program, we're enumerating. We verify the syntax, verified program line. We split the program line because remember it's going to have operator, operand. So we split it. If line at 0 is alpha, that means it's an instruction. Okay, if it's not, it means it's like beta, right? So like if it was like the number 15 at the bottom. So if it's an instruction, get the operator line 0 from the operator dictionary. Okay, if line 0 not has operand, basically if this one doesn't require an operand, operand is 0. We just add a 0. Otherwise, if it's not, we're going to parse the number, verify number and fix negative. And then machine code line, we take the operator, bit shifted. This is what's happening either way. Okay, so if it has an operator, we're getting the operator. We take the operator, bit shift it 4, or with the operand. That's our machine code line. Okay? If it's not alpha, it's data. I think I jumped the gun there. If it's data, just parse the number, verify it, and we're good to go. Machine code line, append to the machine code line. If this part's unclear to you, so first of all, if it doesn't take an operand, the operand is set to 0. Okay? If it does, we just get it. And then if this part's throwing you off down here, consider the fact that like if like the bit pattern for load A from RAM is 0, 0, 1, 0, right? And I want, if this one would take an operator, let's say the operator is 15. I need to make, this is 4 bytes. I need to make it 8 bytes. So how do I do that? I bit shift this to the left, 4, effectively adding 4 bits. I do OR. There's infinite number of leading zeros. I do OR on this. I get 0, 0, 1, 0, 1, 1, 1, 1. There. That's how I generated that machine code line. Append it, and then when I'm done, I just write it to a file. That's the assembler. It's a very simple little program. That's it. Now to run your assembler, you would run it like, okay, Python assembler.py to assemble.esap and assemble.hex. Now I'm using the file extension ESAP for like the ESAP, like the ESAP assembly language. You should all very well know by now that file extensions are entirely like, they're not really that important. It's just a file extension. They're usually there to help people or the operating system. So we can call it whatever we want. You don't have to call it ESAP, you call it text, whatever, it'll parse it. And I save it to a hex file. Again, it doesn't really matter if it's a hex file. Digital will, I think, load it up anyways as long as it's formatted correctly. But you know, I'm using the file extensions nicely here. Any questions about this assembler? So now all I have to do is presumably if I have a text file or a text file that I've called .esap, and I type in my assembly, I should be able to assemble it. Yeah. And it'll generate that hex file. Any questions about any of this? That's the assembler. For the sake of demonstration, let's go here. Topics, programming. Let's go find my assembler. Here's my assembler. And there's that. So I'll open these both up, I guess. So here's my assembler. We just talked about it. It's literally what we just saw. And here is an ESAP script, okay? Or ESAP assembly, I suppose, right? I called it ESAP. This is clearly an assembly. This is the program we already looked at, right? That check 10, right? Load a value, subtract or add 10, or put 10 into B, do the subtraction, and then jump to 6 if it's, you know, anyways. Yeah? Yeah. So if I were to run this, like how do I run this? Well, I would go I don't know if it'll work with Python 2. Assembler and check 10. And in this case, I won't add that second argument, okay? And if I don't, it'll just call it a.hex. Oh, what did I do wrong? Pilot failed to run. Python. How do I have to do .exe, really? No. 3. I might not even have like Python set up on this work computer, so I don't even know.
You might, but then it just forgot somehow. I don't know. It does that. 'Cause I don't like it. 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 'Cause I don't like it.
All right, well, that's what I would have written. And then it would have run and then generated the hex file, which would have looked. I'll find it somewhere. It would have looked like that. It would have generated that. There we go. Cool. Cool? I think that's cool. And then finally, programming with assembly. Like now look, the program, we've already done the programming before. We just did it in machine code. Now we want to do it in assembly because it makes life just a little, like that much easier, right? So with the use of the assembler, we can generate the machine code a little bit easier. You might say, but then we have to run the assembler. Yeah, I know, but deal with it. So once the assembly language is written, it can be assembled in the machine code just by running the program, running the assembler, and then we can load the machine code into RAM. A little bit easier. So we can revisit some problems. So consider the problems that we've already solved with machine code hex files. Instead of writing machine code, we can write the assembly. And if hopefully we see that it's a little bit easier not only to write, but also to understand the program after, like we can look at it. So let's go back to one of those first programs we wrote, 31 plus 32 and then 31 minus 32. All right? So on the left is the assembly. I've got 31 and 32 stored down here. So I load into A, E, load into B, F. I add them together, which overwrites A. I save A to D, so I guess there. I output it as an unsigned. And then I load into A, E again, because we overwrote the 31 that was in A with the result of, with 63, I guess, right? But then I do subtraction, save it to D, output D, but this time it's assigned. There we go. A little bit easier to follow than this, right? I know we're probably familiar enough with the instruction set in the machine code hex values by now that you could figure it out, but like, give me a break. Obviously, this is a little easier to look at. And all we had to do was write a simple little assembler that allowed us to use like the mnemonics. Cool. And then counting. Let's go to that counting forever problem. Like the above problem, it was already discussed in machine code. So how do we count? Well, let's start with like, okay, load into A0, load into B1, but yeah, save A to F, output F, add A and B together, jump to 2. Save, output, add, save, output, add, save, output, add, save, output, add. That's it. There we go. This one doesn't have a halt. It'll run forever, whatever. And then what would the machine code look like? It looks like this. There you go. Pretty cool. And then finally, check 10. We just did that, right? How do we check 10? Well, again, this is a little bit easier. Raise your hand if you've finished the assignment. So if you finished the assignment, do you think when doing the division, do you think using assembly made it easier to do the division? Yes? Good. I hope that was the case. Because it should be. If not, you're crazy. Because obviously, keeping track of the hex values and looking at your code is a lot harder when you have to do additional mental translations than if you're just looking at an instruction that is more clear. All right, so there's check 10. Now, what if we just say count to 10? Here's a tricky one. Let's count to 10. We counted forever before. We also wrote code to do something special if we ever had a value that was less than 10, right, or greater than 10, right? We did some special things. So maybe now, let's combine those two ideas. For a more sophisticated program, let's count to 10. Now, how do we do it? Now, the problem combines two of the things, looping forever and checking if a value is less than 10. Now, I want to be clear that if I explain this algorithm to you, this assembly, and you're like, yeah, it makes perfect sense, it's one thing for it to make sense, and it's another for you to come up with this in the first place. for those of you that did the division, who here thought to themselves, damn, that was kind of harder than you'd think? Yeah, right? That wasn't too bad, I don't think. I hope not, it wasn't too bad, but it definitely isn't trivial. So we did division in software, like we wrote an algorithm to do division. But the constraints of assembly is like what makes it tricky, right? Having to keep track of things. Maybe you need to save things to RAM, load things back, and so on. So all I mean is, it's one thing for me to show you an algorithm and you'd be like, yeah, it makes perfect sense. I understand assembly just fine. And it's an entirely other one to actually write the assembly, right? So let's do counting to 10. Load into A0, load into A0, then I immediately save A for some interesting reason, well, whatever. That's going to come up because of jumping, I believe. Okay, we save A, load into A again. All right, perfect. So we put in 0. Okay, cool. Load into B, 1, add them together, save, overwrite what's in F, output it, load into B, 10, do the difference. If the number is, if the S is high, meaning the number was less than 10, we jump to 2. Load F. Add 1 into B, add them together, overwrite it, output it, do the difference check, do it. And then if we ever get to here and now we are not less than 1, if it ever is equal to 10, we just halt. This is a no op and we halt. So this goes, keeps looping, and then it eventually stops. There we go. And again, there's the machine code for that. That's been assembled by the assembler. Cool. So notice that the count value must be preserved before the subtraction can happen. Yeah, so this was big, right? Like, I needed to save what the current count was before I could do the subtraction. Because if I did the subtraction, I would obliterate what the current count value was, right? Because the current count was an A. I have to save it somewhere in RAM, do the subtraction, which obliterates whatever the count was. So I had to save it to RAM and then retrieve it from RAM. Okay? Yeah. You could say here, was it really necessary because this would start at 0? In practice, we don't know what's in RAM. It's always good to like make sure very intentionally what values are where. Like it would only be the case of this being not necessary if we knew that that value would contain 0 to start. But that's not really a safe thing to assume. Cool. Any questions about that one? All right. Notice the jump. Okay, notice that when running the program, it will appear to count 0 to 10. Right, I said count 1 to 10. It'll appear to count 0 to 10. This is just because the output register always starts with a 0 in it, so you know it starts with that 0. The starting instructions could have been excluded. Yeah, you know, we could have done that, but again, because the simulator starts with zeros in RAM, it's kind of cheesy. However, having clear and intentional code is preferred, like I was saying. Any questions about any of that? Any questions about any of all of this? Because if not, we're done. There you go. Well done. Well done. You better clap, yeah.